My name is Helen Kirchin. I am a PhD student in the UC Berkeley Department of Integrative Biology, and I study how the spatial arrangement of dispersal corridors affects the ability of populations to recover after a disturbance. So I'm interested in if the available corridors are very, very clustered versus very spread out in space. How that movement and ability to move affects populations. And I study that using bacteria in laboratory microcosm systems. So the latest thing I have been working on is a new invention. This is a device that resembles a 96-well plate that I build in layers that have very small corridors cut into each of those layers, so that when you fill it with a nutrient medium and culture bacteria, what you really end up with is a 96 subpopulation, a metapopulation, where the bacteria can move from well to well, and because it's the same size and shape as a regular 96-well microtomater plate, you can do things like read it in a plate reader and do all the things that you would normally do with a 96-well plate, which makes it really useful in the laboratory. So that's what I've been working on lately, and the next thing up for me is going to be making some instructional videos. I really want to share this information with other people and make all these designs freely available so that people can make them in their own labs if that's something that they want to do. For me, I think it matters because these are very difficult questions to approach experimentally. And there have been a lot of different ways that people have tried to approach these questions in the lab, right? So if we go back to 1958, we could think about Huffaker's famous orange and mite experiment, right? That was an experiment where he tried to replicate spatial complexity in the lab with oranges in a big matrix, right? But in that particular situation, you're unable to define the specific dispersal paths, right? In other cases, people have used things like jars with tubes in between them, but that kind of setup gets really out of control in a laboratory really fast. You know, you can only have so many jars in a setup before it's really unwieldy. And so what I've done here is to try to make an experimental setup where you can have large numbers of subpopulations and large numbers of corridors in a system that's totally reproducible, where you can move these corridors on a micron scale and have very, very fine control over the treatments that you're applying. And I think that allows a different type of spatial question to be addressed experimentally that really has not been able, that no one's really been able to do before.